All right, so this will wrap up our discussion of like basic logistic regression. Basic logistic regression, I'm defining as the situation where that y variable only takes two outcomes. So it's kind of wrapping things up. We got some loose ends that we want to talk about. I want to talk in a little bit more depth about goodness of fit tests. I want to talk about what prediction looks like in logistic regression. We call it classification, but kind of broadly it's the same idea. I want to talk briefly about outliers and then give us a very brief discussion about maybe some strategies, or at least a strategy, a pretty in-depth strategy for model building that we can use not just in logistic regression, but actually something we could also use in like a 512 type framework as well. So those are kind of the four loose ends that we have to wrap up. And then once we do so, we'll start next week by talking about different ways of extending logistic regression, in particular extending it to situations where our y variable has more than two outcomes. So let's get started with goodness of fit tests. So we talked about two goodness of fit tests, right? Do you remember their names? Exactly, the Pearson test and the deviance test. Um, and we talked about how they work well when all of your explanatory variables are categorical. They do not work well in the presence of continuous explanatory variables. And the reason why harkens back to those sample size requirements. Right, those sample size requirements, remember, required a certain number of observations for every combination of covariate patterns. But if we have a continuous variable, then and we're measuring it very, very, very precisely or very, very, very finely, right? So maybe we're measuring someone's height, and their height is maybe, right, 6 foot, 1.2 inches. There's only probably going to be one or two people in our data set that have that particular value. So the covariate patterns that involve that value are going to have 0 observations or 1 observation, which means ultimately our sample size requirements can't be fit. And so what we need is we need a different way of approaching goodness of fit in the situations where we have continuous explanatory variables. So there are a few different ways that we might kind of tweak or come up with some different variations of goodness of fit tests to accommodate continuous explanatory variables. We're going to focus on just kind of one, the most widely used one, which is the Hosmer and Limshow test. The Hosmer-Limshow test is actually pretty ingenious. And the way that it works is it creates these categories in this really clever way, and then once it's kind of come up with these categories, it can kind of apply the same sort of basic formulaic approach that we did, for example, in the Pearson test. So how does it come up with these categories? Well, what it does is it focuses not on the x's, but instead on the predicted probabilities. Now remember, the predicted probabilities are functions of these x's. So instead of focusing on the x's themselves, it focuses on the predicted probabilities. For every observation, right, it uses the x variables and of course the model that we fit to come up with predicted probabilities. It then orders those predicted probabilities and then takes those ordered predicted probabilities and breaks them into groups, often of size 10. So right, when we're breaking them into groups of size 10 and they're ordered, we could call those deciles. Right, so we have a group, it's like the observations that have the lowest probability, and then we have a group that's the observations with like the second lowest probability, and then so on and so on. So we can implement this process using the /lackfit command in the model statement, and just like the other goodness of fit tests, large p-values will indicate inadequate fit. Now, like all of our goodness of fit tests, really like every test we've done in this class, or most of the tests, right, this is using this sort of approximate distribution, in this case an approximate chi-square distribution. We need a, quote, large enough sample size to justify this approximation. We need a large enough sample size, right, for our distribution to be close enough to a chi-square distribution that we're justified in using such a distribution. Now, the recommended sample size requirements are that the number of observations in the rarer outcome of y should have at least 5 observations for every parameter being estimated. All right, so this is a function actually of what's going on with the y variable and how many variables are in our model. Now, when I put parameter, I capitalize it to emphasize it's not variables, it's parameters. And remember that a single nominal explanatory variable that has 5 categories, right, has 4 parameters that need to be modeled. Right? So if we had a variable that had 5 categories, we wouldn't count that as one variable, we would count that as 4 parameters, i.e. we would need 20 observations in the rarer outcome of y. So let's take a look at this really quick in the context of an example. We could also kind of work through some of the other stuff, kind of review things that we've talked about in the last couple weeks. So this example comes from our textbook. I believe it's based off a real-life study. The study wanted to know whether the presence of coronary artery disease, which they abbreviated CA, could be predicted by ECG results, electrocardiogram, something like that, which had 3 ordinal outcomes, 0, 1, or 2, as well as sex and age. So age in particular is going to be our continuous variable, and because of that, right, we're not going to be able to fall back on the usual Pearson deviance goodness of fit tests. We're going to need to implement the Hosmer-Limshow tests. All right, so here's some basic code. I'm using that lack fit option to get the Hosmer-Limshow test. We'll take a look at what its output looks like in just a second. So here's our output, right? Always check to make sure, right, that what's being modeled is what you want to be modeled. Here it says the probability being modeled is CA, coronary artery disease, equal to 1. So that's the presence of it, which is what I want to model. So if we look at our response profile, we see it's almost a 50-50 split. We have 37 patients who don't have the disease, 41 that do. So in this data set, our rarer outcome is 0. It's rarer to not have the disease than to have the disease in this particular data set. Now we want 5 observations there per parameter, so it looks like we could fit what? We could fit essentially 7 parameters and still do a reasonable goodness of fit test. So here's our global tests of right, model significance. Notice that they're all very small. So that's indicating that there's strong evidence that at least one of our variables is useful in predicting coronary artery disease. Here is our model equation as well as type 3 p-values for each of our variables. Notice that all the type 3 p-values are below 0.05, so all of those variables add something significant above and beyond the other variables. We have odds ratio estimates to help us quantify, right, the effect of these significant variables on coronary artery disease. And then the very, very, very bottom, we can see the beginning of our Hosmer-Limshow test. It goes on to the next page. All right, so here it is. We could see it broke it into those 10 groups. put 8 in every group except, right, it turned out mathematically to kind of make things work, it had to put 4 in that last group. And so we could basically see, right, it basically says I have these groups. I would expect to see 1.02 people in this first group who have coronary artery disease. And in fact, I observed 2. The next one says I would expect, based on my model, to have 6.98 not have the disease. And in fact, 6 have it. Now notice, right, I mean, remember, these are like, these groups, these 10 groups are ordered based on their predicted probability of being there. And so, not surprisingly, as we move from group 1 to group 2 to group 3 to group 4, this should be intuitive to us. We're seeing more of more people in the coronary artery equals 1 group and less people in the coronary artery equals 0 group. That should be intuitive based on how these groups are constructed. Now, bottom line is at the bottom, where we see our chi-square test statistic, its degrees of freedom, and more importantly, its p-value. So the p-value in this case, well above 0.05. So right, there is strong evidence that that we have an adequate fit to the data, that our model fits our data adequately. Whew. So I think just summarizing, right, all 3 are significant. So evidence that at least one of our variables is useful. All 3 variables were significant. There's our model equation. Now, I think I say this on another slide, but notice the authors made the choice, and I think I just used their code. The authors made the choice of modeling ECG, which took the values 0, 1, and 2. They actually modeled it as a numeric variable, which is saying what? That's assuming then that the difference between the difference in log odds going from 0 to 1 is the same as going from 1 to 2, which, you know, may or may not be true. Something that maybe they know from previous studies, something they maybe know just from industry expertise, from content specialization. Maybe it's something that they've tested previously in the data, but we should be aware that it's an assumption we're building here, and it's not the only way to code ECG, right? We also could have coded ECG as a categorical variable in the class statement, which would have actually fit 2 dummy variables, right? Find and interpret the odds ratio for age. So we could find the odds ratio for age by exponentiating its parameter estimate. So going back to that model equation, the parameter estimate for age was 0.0929. You exponentiate that, you get 1.097. So what does that basically say? How do we interpret that? We would basically say whenever a patient's age increases by 1 year, we expect their odds of coronary artery disease to increase by 9.7%, all other variables held constant. And then last but not least, right, actually the sort of focal point of this example, because we had a continuous age variable, we needed to use the Hosmer-Limshow test, and the p-value was quite large, which is good, right? It indicates a good fit to our data. All right, I think that's it. I think that's 1 down. Check, 3 to go. Oh, whoops, sorry. Not quite done, not quite check. So sample size requirements, we did talk about this. We said we had 37 patients and the rare outcome, so we could fit up to 7 parameters. This model has 4 parameters, so we're good to go. And then a couple considerations. This example was executed to really just to kind of showcase and give us a little bit of experience and practice with the Hosmer-Limshow test, which is what we were discussing. this is true for actually a lot of the examples. I've been doing examples that are very strategic and very targeted, where they're focused on just like one or two key ideas. And maybe by doing so, misleadingly circumventing other important model building details. So, right, a couple issues. One is, right, we kind of jumped to coding ECG as numeric, but as we already discussed or pointed out, we could have done it as categorical. And it's probably, I would maybe encourage us to do our model both ways and try to see which one seems to provide a better fit. Secondly, right, we should have considered the possibility of interaction terms, right? We haven't done a whole lot with interaction terms because we've done a lot of interaction in 512. We've already perfected interaction, so I don't feel like we need to keep going back to it. But I, by the same time, don't want to give the misconception that somehow interaction doesn't matter in logistic regression models. It does. And just like in 512, it's something we should be considering. It's something that we should be testing for, right? And only then moving forward with models in which it's absent. We'll talk more about model building at the very, very end of this PowerPoint. Now, all right, there we go. So one down. Now I want to talk about other ways of evaluating a model. In particular, I want to talk about this idea of classification. Classification is like the categorical version, the categorical analog of predictions, right? We call it prediction in Stat 512. We call it classification in Stat 507. In particular, we're going to focus on some measurements referred to as the C statistic, and also Somers D, which we'll see are just functions of one another. Now, to kind of kick off a discussion of classification, think about how you might do it. How would you use a particular logistic regression model? So you fit a model, for example, trying to predict whether or not a person is like has a disease or doesn't have a disease, has some ailment, doesn't have some ailment. So at the end of the day, right, our model doesn't like say yes or no. Our model has a estimated probability. So our model might say, well, based on all the explanatory variables, I think there's a 40% chance that this person might have the ailment. Based on all these explanatory variables, I think there's a 70% chance that our person might have this ailment. So what we get is we get these estimated probabilities, but in practice, what we probably want to do is we want to classify someone into a group. Do we think they have this ailment, in which case we might give them further tests, in which case we might implement some intervention? Or do we think that they don't, in which case we might sort of wash them out of our healthcare system? How would you do that? Yeah. Well, one possibility is, and I think it's a reasonable one, is that if the estimated probability is, say, 50 or higher, well, that means they're more likely than not to have the ailment, so I'm going to say that they have the ailment. And if their estimated probability is less than 50%, then I'm going to estimate that they don't have the ailment. It's one way of doing it, and I think it's a very sensible way of doing it. Yeah, so as we just said, right, this is one possible idea. Let's kind of go with it for a little bit, and then we'll talk about maybe some other ideas. And so let's do this in the context of our much beloved generic smoking sex disease example, the 507 equivalent of the beloved bear data set, right? You can imagine a bunch of bears, some of which are male, some of which are female, some of which are smoking, some of which are not smoking, right? And some of which have some disease, some of which don't. Now, I took this from I guess probably our week 1 PowerPoint, and it's the predicted probabilities. It's the predicted probabilities. So there's some repetition there. We only have 4 covariate patterns: male smoker, male non-smoker, female smoker, female non-smoker. SAS, the way that SAS kind of creates this data set, creates this redundant line. If you don't want the redundancies, you can subset it by that disease variable. It would make that data set look a little cleaner. You could remove all the observations where disease equals 1. You could remove all the observations where disease equals 0. If you just wanted to focus on just like the estimated probabilities based on X variables. Now, for what we're getting ready to do now, we do need this extra information of that disease equals 1, disease equals 0. So it's actually good. We'll see an example or situation where it's good, where SAS gives us extra information, because that's going to be useful. We'll see in terms of seeing how well this model classifies based on our classification rule that we're applying, this 50% rule. Okay? So there's going to be a lot of tables coming up. And all the numbers for my tables are coming from this output right here. So again, if you haven't already, it might be worth printing the PowerPoints, or at least this slide from the PowerPoints, so that you can reference this slide, right, when we're discussing its content in future slides. So do you kind of see like a little bit of how this works? So if we use that 50% threshold, then what's going to happen is we're basically going to what? Anyone who has an estimated probability of 33%, we're going to predict that those people don't have the disease. Agreed? Because 33% is less than 50. And so what does that mean? It means on that very, very, very first line, we see that there are 6 people who actually had the disease. For those 6 people that had the disease, we're going to predict that they don't, and whoops, we screwed up. Do you agree? For those 6 people, our model combined with our classification rule is in error. However, for the second line, which has 10 people, those 10 people do not have the disease, and our model correctly predicts that they don't have the disease, right? That's kind of what we're going to be doing in the next few slides. Now notice everyone else, all other people, all other combinations of X's have estimated probabilities in excess of 50%. So that means we're going to predict that everyone else has the ailment. And of course, for the ones that in fact do, that's a correct classification. But there are some who do not have the ailment and for who we are incorrectly classifying. Here is the numbers more explicitly. So using the 50% classification criteria, there were 6 people who had the disease that we would have incorrectly predicted didn't. I already said that. There were 10 people who do not have the disease that we would have correctly predicted do not. And then go back to that slide and verify these numbers. But you should be able to see that there's 8 plus 7 plus 24. It's a total of 39 people who had the disease that we would have predicted had it. But on the flip side, there's 8 plus 6 plus 6. There's 20 people who did not have the disease, but we would have incorrectly predicted, based on our model and our 50% rule, we would have incorrectly predicted they did have it. Right? So here we're doing predictions, and we're seeing how well the predictions work, at least as applied to our data set. You need to be able to verify these numbers. If you cannot, That means that there is a big conceptual gap going on. And again, we don't ignore that. Ignoring it is not going to make you a good statistician. I mean, forget tests and homeworks, right? Our goal is to go out and get a job and do our job well. And you're not going to do that job well if you're not understanding where those numbers are coming from. So again, if you don't see where they're coming from, reach out to me. But hopefully you do. Now, that information, that blah, 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 that wall of text in the previous slide could actually be more succinctly summarized with a table that cross-references actual disease status by a predicted or classified disease status. And so here's a table that I put together myself. I just inputted the numbers from the other slide into ProcFreak. All right. So so we could take a look. Right, we have the people that actually have the disease. 45 of them. Of the 45 that actually have the disease, we correctly predicted that they did. So the 39 out of 45, that's 86.67% of our data set. So for 86.67% of our data set, we correctly predicted that they would have the disease. Also, right, looking at that upper row, that no row, those are people that did not have the disease. So the people that did not have the disease, there's 30 of them. We predicted 10 out of that 30 would not. So, right, not quite as good. We have a 33% success rate there. And then the off diagonal kind of shows the errors, right? So we can see that we have 10 plus 39. We have 49 instances of correct predictions, 26 instances of incorrect predictions. Now, typically we focus on that main diagonal, the 86.67 and the 33.33%. These two quantities actually have names. They're referred to as the sensitivity of the test and the specificity of the test. So sensitivity of a test is defined as the probability of correctly predicting when the outcome has occurred, i.e. the probability of classifying as one, the probability of classifying someone has the disease given that they actually have the disease. Specificity is the probability of correctly predicting when they do not. So it's the probability of classifying them as a 0 given that they are a 0. Okay? So again, go back to those tables, but we should be able to verify, and if we can't, we should let me know that for that table, the sensitivity is 86.67%, the specificity is 33.33%. Okay. So we have pretty good sensitivity, maybe not so good specificity. It's good at telling you when people are in the group. It's not so good at telling you when people are not in the group. Now, although it's certainly intuitive to use 50% as our cutoff point, it's not the only way to do it. And we'll talk in a little bit about why we might consider other cutoff points. But for now, let's look at what would happen if we use 30% as our cutoff or 55%. Let's look at both of those. Now, 30% actually looks like this because remember, I forget exactly what the lowest probability was, and if I scroll back, it'll kind of screw up this whole narration, but it was like 34%, something like that. So all of our estimated probabilities, all of them, are above 30%, which means that if we use 30% as our criteria, we are going to predict that every person in our sample has the ailment, which is why I have a 2-by-1 table. Technically, there is a no column, but there's nobody in the no column, and so SAS suppressed it. And so there is what it looks like In this example, if I use 30%, I classify everyone as having the disease. Now 45 people actually had it, so for those 45, we got it right. So that means 100% sensitivity. It's better than it was before, but our sensitivity is 0%, right? We were 0 out of 30 correct when we said that they in terms of predicting that someone doesn't have the disease. All right, so our specificity is 100. Our sensitivity is 100. Our specificity is 0. Yep, there it is. And then here's our table for 55%. Our sensitivity we're going to now see is a little bit lower. It's now 68%, but our specificity has gone up to 60%. Now, you need to be able to verify where these numbers are coming from. Again, this is something I would expect you to be able to do. And again, if you don't have the kind of the deep conceptual understanding to go from the output and generate this table, there's something that's not quite clicking. And that's that higher level understanding, I really do believe, is important for understanding kind of just what's going on with this whole modeling approach. And of course, understanding what's going on is pretty critical to correctly and smartly applying these models. So I leave it to you to go back to that output, right? These are all coming from that original output where we had all the different estimated probabilities. I want you to build this table yourself. That's step one. And then, of course, step two is seeing that sensitivity is that 68.89% and that specificity is the 60%. Yep, so there they are. So we have three tables, right? We had a 30% table, a 50% table, and a 55% table. And if we listed the sensitivities and specificities of those three tables in that order, 30, 50, 55, we would see what? We would see that as that cutoff probability is increasing, as we're going from 30 to 50 to 55, we're seeing two things. We're seeing the sensitivity increase, and we're seeing the sensitivity decrease. And so, right, that tells us that 50% is not necessarily the optimal cutoff, right? That there's a lot of levels that we could use, and that basically different levels, right, different percentages, 30 or 50 or 55, give us different values for sensitivity and specificity, right? That is, one thing is getting better, but another thing is potentially getting worse. And so trying to find kind of that optimal balance is maybe is part of determining like what the quote optimal threshold to use is. Now, one thing that we can do is we could actually not have to focus on just one combination of sensitivity and specificity, as we don't have to focus on just 50% or just 30%. We could actually put together a graph that summarizes what happens for all possible cutoffs from 0 to 100%. That is, we can put together a table that will plot sensitivity and specificity for different classification thresholds. This table is referred to as an ROC curve, right, which is kind of stands for the technical term receiver operating characteristic curve. Now note that it's tradition or convention to actually graph not sensitivity by specificity, but sensitivity by 1 minus specificity. We'll see it actually makes a nicer looking graph. So we got to kind of do a few little tweaks in the proc logistic line to get these things. Essentially, like a plot statement. And that plot statement will ultimately give us. I should say this is I think a little bit of old code. I think that you're going to get this curve as part of the default ODS output. I think that's true. If not, then you have this code to fall back on. So here's our ROC curve, right? So it's different values of sensitivity versus 1 minus the specificity, right? Which is how we get 0 and 0 together and 1 and 1. So 1 is indicating 100%. Remember when we did a 30% cutoff? Like the extreme situation was sensitivity 100%, specificity was 0, right? So typically they're at extremes from one another. One's high, the other's low. But it's nice to kind of make our curve kind of going in this kind of upward direction. And so to do that, we have to plot by 1 minus specificity, not the actual specificity. So we'll see in the next slide kind of that y equals x line, that 45-degree line. That's sort of like the reference line. That's sort of like how we would do if we were just classifying by blind chance, by like flipping a coin. And so we want the line above it, that kind of choppy, kind of piecemeal line above it. That's indicating what's going on with our model. It's got different levels, right? Different classification levels based on our data. Right, so we have 4 covariate patterns. Remember, we have 4 covariate patterns. And so each one of those 4 dots is essentially a plotted point of sensitivity and specificity at that particular threshold or cutoff. Right, so that line plots what it would look like at using our model at different thresholds. And so our thing curves above that reference line. The kind of steeper that arc, the more that thing arches over the reference line, the better our model's going to be. Right? I mean, you kind of think about it. So, like, we're sort of starting at that 0, 0 mark. We're starting at that 0, 0 mark. And we would like to get to that, I mean, we're going to have to eventually get, in terms of the x-axis, we're going to go all the way over to 1. But we would like to do so with the most sensitivity as possible, which means like the ideal situation would be if that line just shot straight up. And so again, it's going to take a little bit of reflection. It's hard to verbalize, but it should make sense to us, right? I mean, the ideal situation would be what? The ideal situation would be as if somehow we had 100% sensitivity and 100% specificity. Agreed? 100% sensitivity and 100% specificity, which would actually represent itself by what? As a point in that upper left-hand corner, right? So like if we had a graph that like shot up as fast as possible to try to capture that upper left-hand corner or get as close to that upper left-hand corner as possible, that's what we would like to see. Now, of course, if it did that, it would then have to curve immediately the other way, And so what it would do is it would create a curve in which this whole unit square is underneath that curve, that the area under that curve would be close to 100% or close to 1. And so what we do is we measure how well a model works by in fact measuring geometrically the area under that curve. We would like it to be as close to 1 as possible. It's not going to get to exactly 1. In this particular case, it's about what? It tells us exactly. It's 0.6941 is the area under our curve. Is that good? Is that bad? We'll talk a little bit about some kind of rules of thumb for determining good values in just a little bit. And then, of course, we can compare that 0.6941 to 0.50, right? That's the area under our reference line. So again, we would expect the area under the curve to be 0.50 if we were just kind of like not even really using the x variables, just kind of classifying people by flipping a coin or by blind chance. Using a model which exploits x variables should do better than that ideally. So we're really interested in how much better than 0.50 did we do. In this case, we did 0.1941 better. Yeah, so, I mean, just the idea I said before, the line y equals x is essentially the reference line of our ROC curve. So as I said, we know the curve will eventually reach 100% sensitivity. That's our goal. We want it to get to 100% sensitivity as fastly as possible, right? So again, both of those bullet points should break it down, and those statements should make sense. We want that curve. It has to reach 100% sensitivity. It has to. And we can determine how well a model classifies based on how quickly it gets there. We want it to get there as fast as possible. And so that implies that we can determine how well a model classifies by looking at the area under the curve. Larger area, more area is better. Now, this is kind of, again, this book, Applied Logistic Regression, is kind of one of the Bibles in logistic regression. The book itself, written by Hosmer, Limshow, and Sturdivant. So, right, there's Hosmer and Limshow of Hosmer, Limshow, Goodness of Fit Test fame. And in their book, they propose this rule of thumb. Now, rule of thumbs often differ from like field to field or company to company. So again, it's very possible you might go into some sort of industry that has different rules of thumb, but in the absence of such, here's like a little something to kind of help us out and give us some type of kind of reference point. So as we already said, area under the curve of 0.50 means no discrimination. This is no better than just using blind chance. Between 0.5 and 0.7 is poor discrimination. Between 0.7 and 0.8 is acceptable. 0.8 and 0.9 is excellent. Anything above 0.9 is outstanding. So, right, we saw we were at 0.6914. So that's like right on that threshold of poor and acceptable. Yeah, as I just said. All right, so note, we can get the area under the ROC curve from our basic proc logistic output. We don't have to create that graph that I made. We could actually go back to just like the default proc logistic output and look under C. The C stands for concordant. Look under the C line and association of predicted probabilities and observed responses. So this is going back to our output. And then if you go down, you see at the very, very bottom there, it says C. And then you see 0.694. So that's our area under the curve. Pretty cool, right? And then sometimes you'll see people, instead of using C, they'll use Somers D. Somers D is just a function. It's like a rescaled version of C. So Somers D is 2 times C minus 0.5. So the idea is, right, instead of looking at the area to the curve, we look at how much better did it do relative to the reference line. And then multiply that by 2. Why multiplying it by 2? Because multiplying it by 2 kind of stretches the scale. So now instead of going from 0 to 1, right, which is what our area under the curve does, now our Somers D goes from minus 1 to 1. All right, so that kind of at least is an introduction into kind of some of the basic points of classification, and kind of coming up with kind of how well a model predicts, right? How well a model predicts for logistic regression is determined by that C statistic or that Somers D statistic. So the two things for us to kind of finish this week's discussion with are outliers and some kind of pointers for model building. So both of these are relatively short. We've kind of finished the bulk of this week's lecture. So outliers. We talked last week about the implications of goodness of fit testing. We said if that goodness of fit test fails, it could mean one of two things. It could mean that our model might need additional variables, maybe some interaction terms, maybe some polynomial terms. It could also mean that there's some outliers in our data that are screwing up the model fit. And so just like in Stat 512, we can and should test for the presence of outliers by looking at model-based residuals. Right, these are kind of like the logistic regression version of these, right, standardized or studentized residuals. There are two types of residuals that are often looked at in logistic regression, and lo and behold, right, here's this sort of little deja vu, a Pearson's residual and a deviance residual. These residuals are defined in ways very analogous to their respective goodness of fit statistics. And if you really are interested in the more explicit formulas, you can look it up in page 235 of our textbook. Now, both residuals are standardized so that anything with an absolute value of 2 we might consider investigating. Now, just like in 512, what do we do when we investigate? Well, we make sure it's not a data entry error. If it is, we fix it. We make sure that it is, in fact, part of our intended population. If it's not, we remove it from our study. However, if it's not a data entry error, and if it is, in fact, part of our intended population, we would be inclined to keep it, despite the fact that it's potentially ruining the fit of our model. Might try some other models, or right, go back to that first bullet point, maybe try adding some extra variables. So we could get the residuals with the influence statement. We can get plots of them with the iplot statement. Again, might be part of the ODS output. But regardless, kind of here's some plots of them. So those stars are right, the residual by observation number. Residual by observation number. And so we can see, right, that it looks like they're pretty much all between 2 and minus 2, doesn't it? I know we got the Pearsons on top and deviance on the bottom. The deviance got a little bit cut off, but certainly looking at the Pearson, they all look between 2 and minus 2. And then looking at the deviance, looks like there's nothing above 2. We'd have to scroll down to see if there's anything below negative 2. All right. So the last thing for us to talk about, and then that's going to wrap up our discussion of basic logistic regression. The last thing for us to talk about is model building. So for pedagogical purposes, to focus on what's new rather than what's old, right? It's still good to talk about. There's still improvements that we could make, but model building is a little old hat for us. It's something that we've already learned how to do in Stat 512, and all of that Stat 512 still holds, like all the different techniques, like the basic ideas, we can still use those. However, and so because of that, I haven't focused on model building. I've focused on these pretty simple models and just kind of assume that maybe this is kind of the final model that we're tweaking or exploring. But right, in reality, in practice, we've already seen examples, particularly in 512 and perhaps in a future take-home test, that we often have many variables, and in that case it's not clear which of them, as well as interaction terms or polynomial terms, which of those should be included in our quote final model. However, as I've already said, the process is very similar to 512, and much of what we've done in 512 carries over into logistic regression model building. We can use forward, backward, stepwise approaches. We could also use a likelihood ratio test to test models without interaction terms against models that do have interaction terms. This is kind of like the logistic regression version of the chunkwise tests that we talked about in 512. So all of that stuff still works. Now, when we talked about the approach in 512, we said very explicitly, this is just one method. If you took 10 different 512 books, they're all going to have slightly different suggested methods for building a model. Model building is not amenable to just like this rigid formula where you do A and then do B and then do C and it's going to be the best method. Every data set is different. That's the beauty of statistics. That's what makes it interesting rather than tedious. That's what keeps us as human beings employed, and what makes it very, very, very challenging for people to write programs that build models. It's why we need to have people build models. So any approach is just a set of guidelines, and no approach is going to be universally better than any other approach. The best approach is one of flexibility. However, just to expose us to different ideas, what I've done here is I've taken the suggested model building approach from Hosmer and Limshow's Applied Logistic Regression Bible, and I've summarized that in the following slides. And I think it's fairly straightforward in terms of how it is. So I don't even know that I'm going to narrate the slides, because I think all I would do is just read what I've written. And to be honest, what I wrote is basically more or less just plagiarized from their book, because it's a very eloquent, well-written sort of synopsis. And so it's up to you, right, whether you want to use this approach, the 512 approach, a blend of the two. It's just giving you some ideas on other ways, right, and this one suggested by some pretty big names in the industry, other ways for building models. So the Hosmer-Limshow way starts with this. It has these different steps. And the first step is select your starting variables. And so they say you start with a careful univariate analysis of each independent variable. It's kind of what we said in 512, right? It's just part of like our descriptive statistics or exploring our data. Do a table analysis of categorical variables with y. So kind of just one at a time, right? Just the first x variable that's categorical, do a table of it in y, look at that table. In particular, look for any cells that have 0 observations, because that can sometimes be problematic and so we might consider collapsing cells, right? So like maybe if you're building a table and you see that like a cell that has Hispanic in it has 0 observations, maybe you combine like Hispanic and Black into just some sort of other category. It's one possibility. And then of course we can't make tables with continuous explanatory variables, so just run a univariate logistic regression model. And keep any variables that have p-values less than 0.25. So this is a generous p-value. But it's like kind of like a little bit of like a first step to maybe wash out a couple variables that just seem very, very, very non-significant. It's like a little bit of a washout test. Then step 2. Kind of like a little bit of a backwards approach, right? All the variables that survive the univariate tests in step 1, they all go into a large multivariate model. And then we use backwards regression to remove variables using a p-value threshold of 0.5 or 0.05, sorry. Step 3, we then check for confounding. So we compare our reduced model, right, after we've finished all that backwards regression. We compare our reduced model to the full multivariate model we started with. And we do that to check to see if any of our coefficients have changed by more than 20%. If any of those coefficients have changed, then that indicates that confounding is present, and we need to go back and add some of the non-significant variables that we removed to adjust for this confounding. We now go back to the beginning to be thorough. We consider any variables that were omitted in step 1. We add those one at a time and double check their significance, now using 0.05, and we add any variables that are significant. In practice, it's probably unlikely that any of them will be. We're now going to refer to this model as the preliminary main effects model. So notice one nice thing about this approach is that we didn't start with all those interactions and polynomials. We started with just the actual variables themselves, and then now we'll start thinking about some of the more complex terms. For any continuous explanatory variables, test for the necessity of quadratic terms. So, right, consider adding some second order, some squared terms. There's also, we didn't go over it, but there are also in logistic regression things called tests of linearity, which are ways of performing tests to see whether we need quadratic terms. But right, one way or another, consider the possibility that our continuous explanatory variables might need quadratic terms. This now becomes our main effects model. Now check for pairwise interactions between all the variables from step 5 by adding them one at a time to the model. So now this is like a little bit of a forward building approach. And only keep or include a pairwise interaction if it is both significant, using that usual 0.05 significance level, and it makes sense in the context of the problem or the context of the phenomenon being studied. Then, right, we can do all the other stuff, right? We have this model. We think it's good. We could evaluate its goodness of fit. We could check it for outliers. We can measure things like its C statistic or Somers D to evaluate, right, how well it classifies or predicts.